Good morning. I'm Rob. I have the pleasure of being one of the 35 people on this paper presenting it. Admittedly, this was my idea, and I dragged a lot of people along the way. At some level, this is probably my most successful project at Facebook, and it just took 5 years to get it published. So, what is this? So, this is an experience paper. What an experience paper means is that it has roughly 10x, possibly 100x more man-hours put into it than the typical grad student paper. And what it means is that the paper is a bare summary of what the work was done, and this talk is a bare summary of the paper. So please bear with me on that. I will talk about the motivation behind this, and the motivation is clear. Basically, if you go to ask a network operator to do something, they basically say no. And testing is a thing that will let network operators say yes more often. And in fact, when they do say yes, it's because they've done a lot of testing in the background. And the question is, how can we make testing easier, faster, better at scale? And I'll use a motivating example of a time that I almost took down a large fraction of the network just to drive the point home. And the problem is, not only is network testing hard, and I'm sure all of you have run into this yourselves, as you go to that scale, it's even really hard. And so we'll try to enumerate some of those things. And then we come up with a model which we call network testing as a service as our solution, and that really is what the Netcastle system is. And we'll talk about the status of the progress with some numbers on scale and traction. We'll have some examples, problems caught, and some example lessons learned. So I don't know if any of you have tried to deploy any of the stuff you're working on, but generally network operators say no. It's a sad fact that most innovative networking research will not get put into the network. And it's some level, it's kind of a failure of our community. And this is not because the research isn't good, it's not because it's not useful or not correct, and it's not because network operators are kind of evil jerks, although there's some evidence of that. The claim is that and this is my personal belief, but I think there's a lot of evidence behind this, that the number one problem in networking is complexity. If you look at this from an operations point of view, what do operators do? Okay, well, they deploy new networks, they monitor networks, they debug things, they repair them, they do provisioning, and every once in a while they get to deploy a new service on top of the existing network. And every one of those operations is slowed down by complexity. So, how do we solve complexity? There's a lot of different ways, but the way that we've tackled with this paper is with extreme software testing. If you can test all of the elements of the network, if you can actually break down the components, if you can elucidate what your requirements are and put them to code in an automated way, then with every change in the network, if you can efficiently brute force your way through it, you can actually prove the network is correct and then be able to change it more often. And that is the motivation of the talk. And the claim is the faster and harder and better that you can test the network, the more quickly you can evolve your network, which is the thing that we all want. So let me give you an example of when this goes wrong. This is legit a problem that I did, and I almost took down a large fraction of the network. On FBOSS, which is FBOSS is the software that Facebook runs on their switches, there is a critical register that decides how many packets can go from the slow path, that is the hardware accelerated piece, from the fast path to the slow path. And we figured out that by default, that thing was set to 1,000 packets per second. And that was actually the limiting factor at the time in our BGP convergence. Because 1,000 packets a second times even full-size packets is not even close to what a modern network is capable of. And so our BGP convergence rate was actually limited by this one hardware register. So there was a number that was 1,000, and all I had to do was write a 0 into it, because a 0 is what the SDK said was to remove the rate limit. What could go wrong? And if folks want to know more about FBOSS, we published a paper in SIGCOMM 2018 about that, and there's a lot of interesting details there. So if you think about the test matrix of what I had to look at, and so the test matrix, we'll just say quickly, is the enumeration of all the variables that you need to think about. So there were 4 different types of switches that I had to make this change on. There were 3 different types of packets. There's actually a lot more, but for the sake of simplicity, we'll say it's 3 different types of packets. There was ARP, there was BGP, and LLDP. And if you don't know what all those are, it kind of doesn't matter. And there were 3 different SDK versions that we had to work on. And the test lab that we had was kind of garbage. Like it's the same kind of test lab that you have in your lab, which is like, there's duct tape and baling wire, and you have to remember that like Lucy last week unplugged this thing and ran the cable through the ceiling and whatnot. And it was this like that kind of standard network test lab that we all know. And because it was that standard type of test lab, you can actually see the permutations here. If you multiply the 3 by the 3 by the 4, you get to 36 different parameters. And even though I tested this a lot, I did not work the full set of this. And what it turned out is there was a bug. It wasn't my bug, it was a bug in the SDK. It turned out that 0, actually for ARP on one of the SDKs, was interpreted as literal 0, meaning there was no traffic going from the fast path to the slow path for ARP. And that should be a really obvious big problem, except for this other piece of complexity, which is we always upgrade the switch in this warm boot mode where all of the settings stay cached in the hardware. And our networks don't change around too much, so the ARP tables basically got frozen in time. So everything looked like it was working. And we actually got to the point where this was deployed to about 1% of the global network before somebody found a problem. And thank God they did, because literally I would have taken down a large fraction of the company. And this is a testing problem. So take this as motivation. Why is network testing hard? There's a long list of things in the paper. These are the things that we eventually got into the paper. I'm only going to cover one of the things. Things I'm not going to cover that I recommend looking at the paper for is resource fragmentation. There's all sorts of crazy sources of testing noises. There's a thing that we call lab rot, which is when the labs just kind of break over time. And then there's human aspects that are hard to model, like resource hoarding. The one that I'm going to cover is I think the key problem, which is what I call an exploding test matrix. So if you took that 3 by 3 by 4 matrix that I had on the previous slide and kind of expand that out to what it looks like in practice. At the time of writing this paper, all these numbers are bigger now, by the way, there were 400 feature tests and 800 feature tests in FBOSS. And that had to be tested across 6 different devices, across 3 different SDKs, across 2 different forms with warm boot or cold boot. And if you multiply all these numbers out, you get a number that's close to 30,000. And every single change now has to have 30,000 different tests run to make sure that that little change didn't have some sort of knock-on effect. And let's just play this out so you can understand combinatorically what this means. So going from 5 different switches we support to 6 different switches jumps the size of that test matrix by about 20%. That's huge with these types of numbers. But that's the easiest kind of change. If you add a new feature, like you've got some cool research project and you just have a switch for whether it's on or off, adding that switch doubles the size of the test matrix. You have a 100% increase. But no new feature is just like this binary switch where it's like magically on or off. There's usually some configuration parameters. And actually, I saw our DC-TCP paper is being here. So when we deployed TC-TCP, it actually had 4 different buffer settings. So at the time of this paper, just trying to play with this now increased our test matrix by another 400%. And you can kind of see how this adds up in a crazy way. And I know a lot of you are thinking, no problem, like you just like don't brute force it. That's dumb. Why wouldn't you use some statistical approximation? Why wouldn't you do something smarter here? And I will tell you, the bugs are not inserted with any statistical model. They're in fact quite pathological, and it takes world experts a long time to even figure out what they are after the fact. And maybe it's just a proof by sour grapes, but we have not found a statistical model or any sort of statistics that will allow us to do anything other than brute force this. And as a side point that this ends up being the point of the appendix, which I highly recommend reading. The size of the test matrix, I will argue, is actually a great approximation of the complexity of your network. And it's an incredibly subtle, but I think a really important point. All right, so what's the solution here? So the solution is we had a centralized team dedicated to the maintenance of a large amount of test infra and test tooling. And the mental model is kind of like the Amazon EC2 infrastructure as a service. You as a developer write a test and push go, and that's this little arrow here. And then on the back end, a large amount of infrastructure takes care of getting your test, applying it to the latest code, getting your change, applying to the latest code, checking out the relevant resources, putting together a topology for those resources, testing, running your test, and then validating, like applying heuristics to decide when your test failed, did it fail because there was an infrastructure problem, meaning a server died that shouldn't have died, or a link failed out, or a disk filled up, or something that really had nothing to do with your test and would be noise to you, versus, no, your code actually was legitimately broken. And if there was an infrastructure error, then it kind of does it all again and rolls it all again, and there's back-end health checking, and there's a lot of complexity on your right side of this. But that's the model, and the critical goal is to free up the individual teams to just write tests. And this lab management aspect, the struggle of this paper has always been to convince people that the lab management aspect of this is a deep, complex, and worthy of research task. Status of the project got started in 2018. There are a bunch of people leading the project currently now. I'm no longer at Facebook. Just some quick numbers that we got past the lawyers. The number of test devices, that is just switches and routers that we test against, is in the order of thousands. Over 500 racks, over 300 megawatts of power. This is just test equipment. We support 20 different teams. So I keep talking about the FBOSS team because that's how we got started, but it's grown and grown. And at least at the time when we cut the paper, and this is probably larger now, we're running 300 to 500,000 tests per day. And as across a fairly arbitrary 140 days that we decided to cut the paper, we found 50,000 failed tests. Now, the exact ratio of failed tests to failed bugs is a bit murky. Sometimes it's 1-to-1, sometimes it's many to one. But you can imagine that is a lot of problems caught before they go to production. Lots and lots of problems that we caught before they went to production in the paper. There are 5 that we call out. I'm going to go through just one of them here today. So a micro loop is a very short-lived traffic loop that happens. And drain it's a load shedding technique where you say, this particular machine, we're going to take it from service. Maybe it needs an upgrade, maybe it needs a maintenance or something like that. And we're going to pull the load off of this thing and distribute it onto other things. So we're going to take this device out of service. And in the specific switch drain that we were doing, basically the BGP router withdraws all its routes. It's an upstream router. There's lots of ECMP around it. It's no problem, right? And basically, the right thing to do is withdraw the routes, but keep the data plane programmed so that the packets are in flight, continue to go where they're supposed to go. Detect when you stop getting traffic, because there's a distributed systems aspect here, like the routes have to reconverge, and then delete the entries from the forwarding information base, the FIB, and then announce to the operator, okay, this is safe to drain. That's how it's supposed to work. What this particular bug found was there was actually a race condition between step 2 and step 3 on the order of 300 to 400 microseconds. And 300 to 400 microseconds doesn't seem like much until you see the size of these routers. This is a massive problem, particularly when you figure out that we're doing hundreds of drains a day around the network for various reasons. And so to catch a sub-second distributed systems race condition is exactly why you need testing of this form. These are real hard problems. In terms of lessons learned, as you can imagine with the experience paper, we just have a lot of them. For the purpose of the talk, I'm only going to get a chance to get into one. Just quickly, the test code itself must be heavily tested. This is, it sounds like a subtle thing, but it's incredibly important. Respect the test pyramid. The difference between infrastructure and code error is really subtle to tease out, and we have some heuristics around that. Do not under-engineer the testing system. This ends up being one of the best engineered systems that I've worked with. Right, like that's, and I'll get into why in a second. You have to, the complex way to manage latency versus completeness of testing, because the developers need early feedback quickly, but you need complete feedback eventually. And this is, again, a subtle point, but the test equipment should not depend on other test equipment. And look to the paper for the details. But so The most important lesson learned from this is that the test signal quality is paramount. So what do I mean by test signal quality? So you run a test and you get an answer, right? And so in this world, we'll define a false positive as the code is actually good. Like the test says the code is good, but it has bugs. And so obviously that's bad, right? Because then you take buggy code and you say, it's good, and you put it in production, and a lot of people get unhappy. Somewhat more subtly, like even a false negative is actually quite bad. So if you say the code is bad when it's actually good, you're wasting a lot of precious developer time. Some of these bugs, even when you have a good test, even when you find out that like the test says the problem's right here, it can take an expert days to figure out what's going on. And wasting people's time for days is not a way to make friends. If you guys need to write that down, let me know. But, and so the insight here is if you're trying to catch problems like a race condition that happens 1 in 10,000 times, there's an interesting parallel to the famous Nyquist-Shannon theorem, like the sampling theorem, which says your code, the test code, has to be more reliable than the code you're testing. Because if you have errors in your test code, you will never find, like if you have a 1 in 5,000 error in your test code, you're never going to find a 1 in 10,000 error in your production code. And so the ratio that, I mean, it wasn't a hard and fast number, but waving hands, basically the test code had to be roughly an order of magnitude more reliable than the test code. And to get to a level of engineering where you have distributed systems, you have funky test infrastructure and whatnot, where you can get there, it is really quite difficult. It's, like I said, it's one of the most extreme engineering systems I've worked on. So in conclusion, what does this all mean? Most of you are probably not running a cloud service provider size network in your lab. For researchers, I would claim like the what and the how of Netcastle is maybe not as interesting. Like maybe there's some interesting details there, but like what I really want you to take from this is the why. Why did Meta invest a huge amount of time, energy, resources, and whatnot into this? Is because this is trying to tackle the biggest problem that they have, which is complexity, and trying to move fast. And then, the next research project you're working on, what I would invite you to think about is what does it do for the size of the test matrix? And the big prize, which I'd love for somebody to do, is to actually figure out what they can take out of the network to reduce the size of the test matrix, to make this a more solvable problem. For operators, you all know this is like vitamins, right? Everyone says you should have more testing and more automation. There's not really news here. When I was there, the FBOSS team was shipping a global update of the software every 2 to 3 weeks because of Netcastle. And I will claim, and there's not evidence to support this other than like a lot of blood, sweat, and tears, that this was not possible without Netcastle. Last, if you liked this paper, definitely read the appendix. It's my crazy rant that we couldn't get anybody to accept, and so we just moved it into appendix, and nobody read it, and it got published. So, and with that, I will take questions. Thank you.